Dauphine, Sarah Merino Aceituno from Imperial, but she is going to go to University of Sussex soon, and Ariane Trescaz, who is currently in Cambridge, but who is going to go to Toulouse soon. Well, I'm a mathematician, and I'm interested in modeling the transition between the passage between discrete models of, say, individuals like fish or sheep into continuum models, into fluid dynamics models. The idea is that to explore the large-scale structures formed by these systems, then macroscopic models can be interesting. They are maybe more amenable to morphogenetic analysis and things like that. So, so in fact, I've been interested for quite a while in alignment dynamics. So there is a very famous work by Vicek who proposed a very simple model of alignment, of local alignment of agents. So basically, if you're looking at these two geese, then they are basically aligned. So they are, they have interacted together in such a way that they have decided to go in the same directions. By contrast, these two gulls are not aligned, of course, but these geese has more than alignment. They're actually the full body that's aligned. And if you compare with this picture of dolphin, where these two dolphins are aligned, by their body are quite not aligned, because this one is actually upside down. So we were interested in the looking at the difference between, in the dynamics between if the subjects only align their velocity or if they align their full body, right? So that's the difference. So I'm going to investigate the difference between what happens if you are just using the Vicek model or if you are using an alignment of the full body. So let me remind you the Vicek model. So that's his original publication in PRL in '95. Actually, it's not exactly formulated like this. Here we formulate the model in terms of continuous time dynamics. In the original paper by Vicek, it was a discrete in time, but okay, I think there's minor difference. So essentially, the features is that the particles are self-propelled. So this is modeled by the fact that you assume all particles having the same constant speed a, uniform among agents, uniform in time, uniform in space, uniform in everywhere. So that's just a constant, and they align with their neighbors up to a certain noise, right? So the each particle here is endowed with a position in RD, so D is 2 or 3 in practice. It could be more if you are interested in, use these models for, say, for instance, data analysis. In this case, there would be a high dimension, maybe, but the velocity is, since the speed is constant, then the only control variables of the agents are just the direction of the velocity. So this is a vector, a normalized vector. And so they evolve in time by just the standard equation x dot equals a times v. But then the velocity is updated over time by a combination of two effects. First, there is a noise, which is here modeled by a Brownian motion with intensity tau. And second, there is an alignment, and the alignment is computed as follows. So the agent xk looks around in a small disk of radius r, check the other agents, compute the mean velocity, and then normalizes its mean velocity into a direction. So here is the sum of the velocities of the agents in the small disk around xk. So that's this vector jk, and then you normalize the vector jk, provided it's non-zero, so the occurrence of a zero vector, a zero mean velocity is, say, of measure 0 in configuration space, so we assume rule out this occurrence, so you get a vector of norm 1, vk bar, and you plug it in here, multiplied by a factor nu, which measures the intensity of the alignment force, right? So in order to preserve the fact that the vector v is of norm 1, you have to apply, to make sure that this vector dvk is orthogonal to vk, and that's the role of this projection onto the orthogonal to vk, right? So that's, there is a small mathematical subtlety here, because you have to interpret this product as in the Stratonovich sense and not in the Ito sense, in order to ensure that the dynamics remains on the sphere. But that's just a very, very technical detail. So basically, the dynamics in velocity is a there are two antagonist phenomena. One is noise, which is a defocusing mechanism, and then there is alignment, which is a focusing mechanism. So that's so yeah. So there's in the original paper by Vikshek, you can show that if the noise intensity is not too large, then the particles choose a global orientation after some time, and all move in the same direction, right? And there is a phase transition when tau increases, or when the density, actually the density is also a bifurcation parameter. If you decrease the density, then you have the formation of the aligned state. So let me just give you a short movie of what's happening. So that's, yeah, for these are the case where the noise is a little bit larger than the critical noise, so you have no formation of structures. In the case where the noise is below the critical noise, then you have formation of clusters of aligned particles, right? So this is a typical outcome of this model. And as I said, we wanted to sort of use the inspiration given by the Vikshek models to analyze what's happened when you try to align the full body. So here, in order to model the full body, you so the Q will be introduced a bit later, but essentially a body is a frame. A frame is represented by a rotation from a reference frame. So basically, the control variable of the agent is a rotation matrix. So it's an element of the special orthogonal group, and the direction of motion is supposed to be the first axis of the frame. So that's the image of the first axis of the reference frame by the rotation. So that's the direction of propulsion. So that's the rotation applied to the first reference axis. So the velocity of the agents is a times this rotation times E1. Now the evolution of the rotation is basically given in the same, essentially the same principle as the previous one. So you have some noise, and then the alignment is computed as follows. So again, like in the case of the Vikshek model, you compute the average, say, the average matrix that you get in summing all the rotation matrix of all the agents nearby, that you get a matrix which is not a rotation, and you restore a rotation by using the polar decomposition. So essentially, that polar decomposition means that whenever you take a non-singular matrix M, then there is a unique rotation matrix such that there exists a symmetric matrix, and you can write this matrix M as the product of the rotation and the symmetric matrix. And you can actually choose to write in the different orders. Maybe the symmetric matrix would not be the same, but the rotation matrix would be the same. So the rotation matrix is some intrinsic object related to this non-singular matrix M, which we call the polar decomposition of M. That gives you the AK bar. And we assume that the dynamics is actually given by, so the noise and the alignment term is taking this polar decomposition of these arithmetic average of the matrices in the neighborhood. And in order to preserve the fact that this dynamics remains in the rotation group, you again have to projection the tangent space to the group. So there is a projection onto the tangent space to the special orthogonal group at the position of AK in order to preserve the dynamics on the rotation group. Again, you have to be a Stratonovich to ensure that the noise term is not going to actually drive you away from the group. So that's the rule for the body alignment. And now let me give you some simulations that have been done by a computer science student who enjoyed working on these rotations. So essentially, you see the clusters forming like in the Vic-Check model. The colors indicate that so there are three sides. So we are looking at particles which are bodies. So we color, say, red, blue, and green, three sides, and the white is the back. So whenever you see the same color, that means the same body frame orientation. So you see that as the clusters form, then the agents also align their full body. However, between different clusters, you may have different orientations. I forgot to mention that the motivations for looking at this is, of course, that, for instance, in control of, robots or drones or things like that, this kind of dynamics might be actually quite useful. On top of actually being also interesting to actually in analyzing how birds in flocks actually align, because the flight dynamics in the flock may be very important, and the fact that the birds are not only vectors but are frames in some sense, that might be important as well. All right, so the questions that we wanted to ask when I see the two videos, I do not see really much difference, in the sense that the question that we wanted to ask is there a difference in the, apart from the fact that you introduce the body and that the body orients itself, but for the directions, for the direction of motion, is there a difference between the two dynamics? Is the body alignment dynamics just a Vic-Check kind of dynamics plus superimpose a kind of a motion of the body, or is there a true interaction between the body dynamics and the direction of the particles, right? So this is basically the questions that are written here. And from the videos, this is not clear. And so one of the answers that, one of the methodologies that we thought could be useful to answer this question is actually to try to develop coarse-grained hydrodynamic models for the two models and see if they are the same or not, right? So that's the motivation for doing this. And yes, so I learned from interactions with friends from mechanics, fluid mechanics, that dealing with rotations is more easily done in 3D using quaternions. So this is what we did. So let me just flash a very short slide about reminding you what's a quaternion. So quaternion were invented by Hamilton, at the time where people were struggling trying to extend the complex numbers to 3 dimensions. So eventually Hamilton came with a solution that actually the natural extensions of complex numbers is not to 3 dimensions, it's to 4 dimensions. So he came up with this idea where you actually represent quaternion with as element of a 4-dimensional space, but the first component represents a real number, and then the 3 other components represent, say, 3 different imaginary directions. And so these I, J, and K are numbers that satisfy these multiplication rule, and the quaternions form a division ring. So it's non-commutative. And so this is the real part. All this forms what's called the imaginary part. So the imaginary part of the quaternion can be is isomorphic to a vector in 3 dimensions, right? So in fact, usually if you are dealing with a space of 3 dimensions, you identify it with the imaginary component of a quaternion, or if you like, imaginary quaternions are isomorphic to the 3 space. There is a concept of conjugation by just taking a minus in front of the imaginary part. You have of course, the usual scalar product in R4 is actually the multiplication of a quaternion by its conjugate. So the unitary quaternions, which are those which have a product with their conjugate equals 1, is isomorphic. Is isomorphic with 3 spheres, the sphere in R4. And these unitary quaternions have the nice properties that they actually encode rotations in the following way. So if you're looking at a unitary quaternion, you can write it as this. So you pick up a vector a unit vector in S2 now in the 3 space, a unit vector in R2, and a number in 0, 2 pi, and you form cosine of theta over 2 plus sine theta over 2 times this unit vector. And this unit vector being thought as an imaginary quaternion. And so that means you're forming a quaternion. And so this quaternion operates on 3 space like so. So you take a vector in 3 space, you multiply it, you considering as an imaginary quaternion, and you operate with Q on the left side and Q star on the right side, taking imaginary, that you get another vector in 3 space, and that's just the rotation of angle theta and axis n, right? So this is related to what's called the Rodriguez formula, for those who know that, where basically you encode essentially a rotation in 3 space by its axis and its angle. Be careful, this kind of representation is not valid in more than 3 dimensions, right? So this is why this approach is only restricted to 3 dimensions. And so the way you have a mapping from unitary quaternions to rotation matrices, it's not actually 1-to-1, because 2 opposite quaternions actually represent the same rotation. What's nice is that it's a group isomorphism, in the sense that if you take 2 quaternions, take the product, the rotation that's encoded into this product is the same as the product of the 2 rotations. So it's very nice. It's a very it has a lot of algebraic rich algebraic structure. There is a whole hundreds of papers and which develop this analogy. I'm not going to touch on that, but I'm going to use the quaternions to represent the this averaging in body frame. And you see that what's the key point is that if I want to imagine that if I remember I have this average matrix here, A bar, which is kind of the average rotation of the different rotations that are described by here. I could imagine that with some hope, the quaternion representing this rotation matrix will be some average of the quaternions representing these matrices here. But there is a difficulty here, is that 2 opposite quaternions represent the same rotation. And if I average, say, Q and minus Q, of course I get 0, right? So that means that I cannot just do some standard averaging of the quaternions to represent this averaging of rotation matrices. I have to use the fact that the 2 quaternions, the 2 opposite quaternions, represent the same rotation matrix. And this is reminiscent to what's happening when you're looking at liquid crystals, when you represent the direction of the rod-like molecules by a unit vector. You can actually take one unit vector, its opposite, It's not. It's going to represent the same molecules, right? So we have, in some sense, we were inspired by this, and we thought that what could work would be to actually look at nematic alignment, right? So this is what we did. So now if I represent my model in terms of quaternions, so instead of having a rotation matrix, I have a unit quaternion that represents the body frame of the subject, right? So if I, looking at the first, the direction of the motion of the, say, of the bird, I will have to operate the quaternion onto the first direction vector. So this is the direction of motion. I'm going to call it E1 of qk of t. So the motion of the bird is represented by xk dot is equal to a E1 of qk of t. And now the difficulty is to say how I'm going to average the quaternions in order to take into account the alignment between the various neighbors, right? So for the noise, it doesn't change much. Actually, there is a subtlety. There is a factor 2 that you have to divide the noise in order to get the same as before. But for the alignment, what we do is actually we are exactly doing like I said, and we are using nematic alignment. So in fact, the alignment force is going to be looking at qk bar, which is going to be, the average quaternion, but pre-multiplied by the inner product of qk and qk bar, meaning that you are going to, if qk is in the same, say, half space as qk bars, then you are going to pick up qk bar. If it's in the opposite one, then you are going to pick up minus qk bar as the alignment direction. So that's typically the force that you will get from the nematic alignment. And what is qk bar? Well, that's we have actually decided to take the leading eigenvector of the Q tensor. So you, in liquid crystals, you are interested in forming the sum of the projection matrices onto the various directions qj. So the projection matrix is just the tensor product of two copies of qj. That's a projection onto qj. Remember, qj is a vector of norm 1, right? You sum all these projections onto of the particles which are in the neighborhood of your given particle xk. Then you get a symmetric matrix, and that symmetric matrix is called the Q tensor of the particle k. In fact, in the liquid crystal, you remove the trace. But here, I mean, for reason due to the incompressibility of the surrounding fluid, I'm not going to do that. That doesn't matter. And I'm going to define the nematic alignment direction as the leading eigenvector of this matrix, provided it exists. So, but the space, I mean, the subset of the symmetric matrices in which the two leading eigenvectors are the same is of, say, zero measure. So generically, there is a unique leading eigenvector, or normalized, actually, there are two. There is qk bar or q minus qk bar, but I don't care, because here in the definition of the force, you know, it's invariant by changing the sign, right? So I pick up either one or the other, it doesn't matter. And again, yeah, I have to take in the dynamics the projection onto the normal, to the vector qk, in order to preserve the fact that the qk here is a unit vector, is a unit quaternion, right? So that's basically the dynamics, the previous dynamics written in terms of quaternions, right? So the thing is that it's actually funny, actually, that we were able to prove that the previous dynamics written in terms of the projection matrix, or the rotation matrices, and the dynamics written in quaternions is actually identical, right? They are identical, right? So, so this is really how you write the previous model in terms of the quaternions, right? So the interesting thing here is, by using the quaternions, that you have transformed the problem of finding an average rotation, so the average, so computing an average on the rotation group, into computing the average over symmetric matrices. So computing the nematic average, I would say, over symmetric matrices, right? And in some sense, you've gained, because symmetric matrices form a vector space, and the rotation group doesn't form a vector space. So in some sense, by using this mapping, you have sort of rectified the problem, right? So this is an interesting property. Unfortunately, it doesn't. The similar is not true for higher dimensions, right? So that's all right. So I was promising to give you the hydrodynamic models. So first, in order to derive the hydrodynamic models, what we do usually is first to write an intermediate model, which is a kinetic model, in which instead of looking at the particles individually, you're looking at the particle probability distribution of a particle being at position x and, say, quaternion q. So here is a probability density on R3 and on the unit quaternions, right? And so if you translate the dynamics, the discrete dynamics, into the dynamics of this object, using, for instance, similarity with Ito formula, then you will get a kind of a Kolmogorov-Fokker-Planck equation where the drift is in the direction of, is represented by this operator. So this is just the drift in space at velocity a times E1 of q. E1 of q is the direction of the first vector of the frame represented by q. And then you have the noise term, which results into a Laplace-Beltrami operator on the three sphere. And there is the alignment term, which is this derivative in q space, and the force curly f is constructed as before. So you have qf bar, the average, the average quaternion, the average mean quaternion direction, times qf bar, projecting on q perp in order to preserve the normalization of q, and qf bar is now the leading eigenvector of the analogous q tensor, but with this continuum description where you integrate over x prime and q prime, right? So you have essentially the same representation as before. So then once you have this, then actually the passage from the discrete model to this is not entirely trivial. You have actually to prove something because the particles are interacting. And so you're basically, what's written here is essentially true when in the limit of the number of particles going to infinity. And here, yet in this case, it's not completely clear because, in fact, I push this under the carpet by the fact that the linear, the existence of the leading eigenvector, you have in some sense to prove that at any time your dynamics is away from the cases where the leading eigenvalue could be double or multiple, right? So it's not, the proof is not yet available, but we are confident it's possible to have it. And so then we have to change essentially what we are doing when we are looking for continuum models. We are looking at large scale, so we have to rescale the problem, basically meaning that we have to dilate the variable t and the variable x, and that makes an epsilon, a small parameter, which is the ratio of the scales, appear, or rather 1 over epsilon in front of these two terms, which means that essentially at large scale the dynamics will equilibrate the antagonist effect between the noise and the alignment, and at every time and space, then you will sort of evolve with this fixed equilibrium, not fixed, it's within an equilibrium of these guys here, right? So I don't have much time to get into the details. Let me just give you the shape of this equilibrium. So if you assume that locally at any time and any space, the noise and the alignment equilibrate themselves, then basically then you get that the distribution, the statistics of quaternions is given by this probability in Q. So Q bar is a kind of the is an alignment direction, is a nematic alignment direction. At any instant in time, you have an alignment direction Q bar, which is picked up by the system. It's kind of a symmetry breaking, but this Q bar may depend on space and time. So the key question is to find this vector Q bar as a function of space and time. And the macroscopic equations are precisely giving you the evolution of this quantity. There is another quantity that you also need to find, because you have a dynamics in space and time, which means that your equilibria are given by this distribution, but they are weighted by the local density of particles. So at any given time, you have to find what's the density of objects and what is their mean nematic alignment, right? So I won't give you the details how you do that. Just to flash one thing is the difficulty is that you don't have momentum conservation in the system. Usually when you have such structure, for instance, in gas dynamics, you're going to find the mean velocity by applying momentum conservation. Here you don't have such momentum conservation, and so you need really to find a different method in order to overcome the lack of conservation. And then there is a trick that we have. So usually these conservations are known in kinetic theory as a collision invariant. So basically momentum conservation leads you to a collision invariant, which allows you to find the U, but here we don't have enough collision invariance. So we were able to show that actually there is something that replaces the notion of collision invariant, which we call generalized collision invariance. It's not really a conservation. It's a kind of a pseudo conservation. So in some sense, it's a conservation that's on a smaller, in a restricted space, and that allows you to close the system. However, these generalized collision invariants are not simple functions, like for instance the momentum in the case of the momentum conservation. In particular, they are found through the inversion of an elliptic equation, suitable elliptic equation, and it's actually the hard thing, and what helps us, the only thing that prevents us to develop a higher order version of the model is the fact that we don't have this equation for higher dimension. Here we're really using the quaternion structure actually to get this equation. So that's the trick. But once you have done that, then essentially you get a system like so. So you get a mass continuity equation. So here is basically the mean direction of motion. Q bar is the quaternion that represents the mean body alignment of the agents in the neighborhood. And then you have an equation for the evolution of this mean body alignment, which is here. I'm not going to comment this in complete detail. I'm going to, now in the few minutes that remain, actually, rather than giving you the full detail of the model, rather compare with the Vic-Sheck model. So in the Vic-Sheck model, you can do the same thing, and this is the dynamics that you get. So you get a continuity equation, and then the equation for only the direction of motion now, which is the mean direction of motion, which is a vector of norm 1, because it's a mean direction, satisfy these equations. It looks a little bit like the momentum conservation in gas dynamics, that there are several differences. First, the fact that the mean direction is constrained to be of norm 1 implies that you have to project here the pressure term on the orthogonal to omega, right? So that's the one first difference. The other difference is that you have a different speed between the convection of the mass and the convection of omega, which is actually, which can be seen as a signature of the lack of Galilean invariance of the model, right? So this is basically what you get from for the Vic-Sheck model using the same methodology. So now if you go to these body frame alignment, one thing that you could do is actually write an equation for all of the vectors of the frame. So omega is the direction of motion, and u and v are the two other directions, say, for instance, the direction of the wings and the direction so the vertical direction, right? So it turns out that you can do that, and you get a rather complicated system. Still, actually, it is constrained by the fact that omega, u, and v have to be a frame. I'm going to concentrate only to make the comparison with the Vic-Shack model on the first two equations, because omega is the direction of motion. So here is the difference. So in the case of the Vic-Shack model, you get this. And in the case of the body frame, for the direction of motion, you get an extra term, right? And that extra term can be expressed like so. It's actually called r because it looks like it's related to the curl, the rotational of the axis of the rotation, right? So its formula is actually given by here. It's omega grad omega plus u grad u plus v grad v. Okay, so you have this term. So again, this is convection of omega. This is action of the pressure gradient that turns, let people turn away from the high values of the density. And then this is another term that's not present in the case of the Vic-Shack model, which essentially takes into account the fact that if you have a field of, say, frame which is around yourself, which is not homogeneous, then this is induced actually a rotation of your direction of motion. So in fact, there is a component of the change of direction that's due to the inhomogeneity of the frame around. So if I compare the two models, I see that there is an additional term in the body orientation model. So I conclude that there is an actually net effect, non-trivial effect of the body frame orientation onto the choice of the direction of motion, which was not obvious from the simulations, right?
Could you remind me what U and V were in that?
So this U and V are, so I just, instead of describing the rotation by a quaternion, I describe just by the frame. So omega, U, and V are the three vectors of the frame.
Nice.
Right? So this is the conclusion, and I think I'm going to stop now, is that in fact there is actually, yes, a non-trivial effect of the body alignment on the dynamics of the particles, and this we were able to actually show it by using the coarse-grained models. And yeah, so just a slide of conclusion and perspective. I think that the model is interesting because well, it provides actually an intriguing dynamics. Even the mean field model sort of using quaternions. There is almost nothing known about this model, so there is no analysis, no existence proof, no proof of convergence. We are actually conducting numerical simulations of this model. Even these solving these models where the unknown is a field of matrices is not something that's usual. And of course, there is the still open problem of finding what is the model in higher dimensions. That can be seen as a theoretical exercise. However, I spoke to a control theory person that's actually here in Cambridge, and he told me that within the big data, frenzy, there is actually a need for finding, models that to actually find averages or find statistics on data that are high dimensional and have a geometric structure, like being a rotation matrix or any other geometrical structure. So this gave us the motivation actually to investigate the high dimension case. But it's just right now an open question. I thank you for your attention.
First of all, what happened to the interaction strengths, to the alignment strengths, and to the noise, and to the radius in your continuous model? I assume the radius was
oh yeah, so I skipped that slide.
By density.
So essentially, Yes. So the scaling is such that basically the noise and the alignment strength are, say, very large, right? But the ratio is order 1, and that's basically that gives you this is what gives you the variance of the distribution of Q around the Q bar. So the variance of the when you're looking at this object, the K here is the ratio between the alignment frequency to the noise, right?
And the radius is sitting.
And the radius, and this is the other thing, the radius is actually order epsilon. So in the end, so that means that in the limit we are looking at local interactions. This is actually what enables us actually to say that locally you have an equilibrium. In fact, what we are able to do is actually take larger interaction radii of the order square root of epsilon. So this interaction region is small, but it's actually becoming comparatively larger than, say, the mean-free path, I would say. And in this case, what you get is an additional diffusion in the final equation, right? So here you get another diffusion term in Q bar. So there is a kind of a viscosity effect which is added if you are doing this other scaling.
So then, what's the relative role of K, your ratio there, and density, which I suppose is playing now the role of,
so you're touching
promoting order?
Yes. So you're touching actually a very important question. Here we cheated in the sense that we have ruled out any phase transition. So this is a model only for the aligned state, and the reason for that is that here when we choose to take the interaction driven by the leading eigenvector of the tensor and not by the Q tensor itself as you do in liquid crystals, then we rule out all phase transitions. That's done on purpose because the handling of phase transition in this case is already in the case of the liquid crystal, which is three-dimensional, is at least theoretically rather tricky, but in four-dimensional the question is not fully settled.
So this doesn't support isotropic states, is what you're saying?
Sorry?
This does not support isotropic states?
No. I can tell you what I would get in the isotropic state. In the isotropic state, I would get a diffusion model. I would get so there would be only the equilibrium would be only supported by density. There would be, because the rest is trivial, is isotropic distribution, and the density would satisfy the nonlinear diffusion equation. So the difficulty, and this is something that we are actually also currently doing, is actually to have the two kinds of models crosstalk across interfaces between the two regions, right? So this is a problem that's still open in this analysis. So we do not really have a theory of what would be the interface conditions between the region of aligned state and the region of disorder. So that's.
I suggest we continue this lively Q&A with some coffee. I'll thank you again.